Hello, y'all. This is Darrell Lee Berry Jr. Back with some more linear algebra, preparing for my exam on Thursday. Be sure to like, subscribe if you haven't already. If you have any questions, you can join me on Discord at another time, or put your questions in the live chat here. Uh, in the future, I may start having some question and answer sessions on Discord, so be sure to sign up. When enough people are there, I'll start scheduling that. We'll proceed with where we were in chapter 2.1, and we'll just continue with this section here. So let us start with example 3. It says to see an extreme example, consider the 1 by 3 matrix. Example 3. B equals 1, -1, 2, right? So AB, which is 1, 3, and 3, 1. So I should have a 1, 1. So that's going to be 1, 2, 3, and 1, -1, 2. So that equals 1 minus 2 plus 6 equals, and then let's go the A, which is 3, 1, and 1, 3. So we should end up with a 3 by 3. So that's 1, -1, 2, 1, 2, 3. So that equals 1, 1, -1, 2. So each one of the columns becomes still a column. 2, 1, -1, 2, and 3, 1, -1, 2. So that's 1, -1, 2, 2, -2, 4, and 3, -3, 6. All right. That's what the book has as the answer. So it's always good to check what the dimensions should be that will guide the process. And every column in the right one becomes a column in the new one. So we have one column in the right one, so that becomes one column in the new one. And here we have just one column. 3 columns in the right one, so that becomes 3 columns in the new one. Even if you start with both A and B as n by n matrices, the products A and B, A, B, B, A have the same shape but need not be equal. Example 4. A equals 1, 2, -3, 1. and B equals negative 1, 0, 1, 0. AB equals, so I have two columns, so I'll end up with two columns. So negative 1 plus 2, 3 plus 1, 0, 0. So that equals 1, 4, 0, 0. And BA equals negative 1, negative 1, 0, and 1, 0, 1 plus 0. And then we have negative 2, uh, yeah, negative 2, 0, and 2, 0. All right, so that was pretty difficult doing it written down when it's written down in the wrong direction, but it's doable. When and only when A is a square matrix, we can multiply A by itself, obtaining A squared, which equals A times A. A cubed is A2 times A and A times A2, etc. In the last examples of chapter 1, section 6, the vectors xk are obtained from the initial vector xo by repeatedly multiplying by the matrix A, so that xk equals AK xo. I'm not sure about that one. Oh, I see. So they have the vector xo, and they multiply it by A, and then they multiply the result of that by A. But that's the same thing as squaring the matrix and then multiplying it by the vector. So it seems to be saying that AK equals A squared K, which equals A times AK, doing the parentheses first according to PEMDAS. Example 5, there's an interesting way to interpret matrix powers in terms of directed graphs. Starting with the matrix, we draw a graph with three nodes or vertices and aij directed edges paths from the node I to the node j as shown in figure 1.1. For example, there are two edges for the node 1 to 2, two edges from the node 1 to node 2. We draw a graph with three nodes or vertices and aij directed edges or paths. So 9 paths. 1, 2, 3, 4, 5, no, 6 paths. All right, so this is not clear here. I don't remember any homework anywhere similar to this, so maybe I'll skip this part. That's confusing. I'm gonna have to come back to that one. Trying to make sure I get through everything. So a squared is a times a cubed is a squared times a again, and so forth. And in particular, there are 169 7-step paths from node 3 to node I. Hmm. So this seems to be directly related to probabilities. I'm gonna need some help with that one. I don't want to spend too much time trying to figure it out. We see that in general, matrix multiplication is not commutative. However, it does have the following crucial properties. Okay, let In denote the in the matrix with ones on the diagonal and zeros elsewhere, as illustrated on page 61. It's proposition 2.1. N equals is an N by N matrix, which equals 1, 0, 0, 0, 1, 0, 0, 0, 1. That's going to be sub N. So that's the identity matrix. Let A and A prime be M by N matrices. Let B and B prime be M by P matrices. Let C be a P by Q matrices. Let C be a scalar. So A is M by N. A prime is M by N. B is N by P. B prime is N by P. C is P by Q. So it could only be multiplied to B prime or B or B prime. N can be, B's can be multiplied only to A. And C is a real number. Then so you start with the given, then 1. A times the identity matrix equals A, which equals the identity matrix M A. Interesting. So A times the identity matrix equals A equals the identity A times the identity matrix with the number of columns equals the same thing as the identity matrix in the front with the number of rows. So IM is an M by M matrix. Okay. So this is M by M. Makes sense. And this is M by N. All right, so all of this is just matching up the appropriate rows and columns. But still, one is on the diagonal, but it's just the only way the proper number of rows and columns line up for the matrix multiplication is for it to switch over like that. So 2, A plus A prime, which are the same dimensions, times B equals AB plus A prime B, and A B plus B prime equals AB plus AB prime. This is the distributive property of matrix multiplication over matrix addition. 3, C A B equals C A B equals A C B, and 4, A B C equals A B C. This is the associative property of matrix multiplication. So notice that they're in the same order, ABC, ABC. but the scalar could be anywhere. The scalar can multiply by anything. You could multiply the scalar by one of them, by the first one first. You can multiply the matrices first, or multiply the scalar by the second one first. That doesn't matter. Right? So they're going to prove that. Okay, so this is actually worthwhile to go to the proof, for the proofs on the exam. We prove the associative property. I'll leave the rest to the reader in exercise 4. Note, note first of all, there is hope. AB equals an M by P, because you have M, N, and N, P, makes sense. And C equals P by Q, so they can be multiplied. So A, B, C equals a M by Q. Similarly, A is an N by N, BC is an N by Q, so ABC is an N by Q. Associativity amounts to the statement that ABC equals ABC. ABC equals A, BC for any column vector C of the matrix C. That makes sense. Because this is going to be multiplied over column by column. So a B C vector equals a B C vector. For any column vector C in the matrix, to calculate the jth column of ABC, you multiply AB by the jth column of C. That's right, because the AB becomes one matrix. That is a MP matrix that multiplies properly with that. To calculate the jth column of ABC, multiply A by the jth column of BC, which in turn is a product of B with the jth column of C. His wording is cryptic, but I understand because of the use of the dimension thing here, which is very helpful to me. That B1 through BP, which are column vectors, denote the column vectors of B. We recall Cesar Cruz observation on page 53 that BC is a linear combination of C1, B1 through so on and so forth. So B is the row vector. No, B is the matrix. That's right. And it's a linear combination of column vectors, BC. Wonder why it's a plus though. I need to go back to proposition 5.2 of chapter 1. Let's go to page 53. Oh, I see. This is A times X. They must have left that out or something. Well, that's what they mean. That's not a scalar, that's a vector. I thought that was a scalar. Okay. It's the matrix B times the vector C, times the vector C. So yes, that would be a dot product, so it'll sum. So it's C times all the B vectors. Okay. And B1 is the first column, second column, so forth. Okay. Come with them. A, B, C. A, B, C, right, is A, B, C. This is an important conceptual point. There is an important conceptual point underlying this computation as we now study. Through chapter 1, we thought of matrices simply as an algebraic shorthand for dealing with systems of linear equations. However, we can interpret matrices as functions, hence imparting them to the geometric interpretation and explaining the meaning of matrix multiplication. Multiplying the m by n matrix A by vectors x and Rn defines a function, right? So Ax and A is an m by n and m by whatever is an Rn. So that means that's the number of rows that vector has when it's written as a column vector. It's a function. So it's transferring that vector from Rn to Rm, because that's going to equal B. And that is an m by whatever that second thing is. So that is in Rn because it has n number, Rm because it has n number of rows. So we see that a matrix transforms something in an n space to an m space. Something from the n space of the matrix, or whatever the space of the vector is being multiplied to an m space, which is the first space of the matrix. So it transfers from the n space, from the second, from the column space to the row space, if you could say, right? And this is given by mu a as a function of Rn to Rm u a x equals a x as a function. The function mu a has domain Rn in range Rm. And we often say that mu a maps Rn to Rm. All right? A function f x to y is a rule that assigns to each element x the domain x an element f of x of the range y. We refer to f of x as the value of the function at x. We can think of a function as a machine that turns raw ingredients or inputs into products or outputs, depicted as a diagram such as on the left of figure 1.2. In high school mathematics and calculus classes, we tend to visualize a function f by means of its graph, the set of ordered pairs xy with y equals f of x. The graph must pass the vertical line test for each x equals x naught in the space x. There must be exactly one point x naught y among the ordered pairs, right? We say that function is one-to-one if the graph passes the horizontal line test. For each y equals y naught in the space y, there is at most one point xo among the ordered pairs, so no two x's give the same y. The function whose graph is pictured on the right in figure 1.2 is not one-to-one. Seems one-to-one to me. Quasi. There's two x's that make the same y. Another term that appears frequently is this. We say f is onto or surjective if every y in the space of y is of the form y equals f of x for at least one x in the space of x. That is to say, f is on 2 if the set of all its values, often called an image of f, is all of y. When we were considering linear equations ax equals b in chapter 1, we found constraint equations that b must satisfy in order for the equation to be consistent, which we found. Vectors b satisfying those constraint equations are in the image of UA. The mapping UA is on 2 precisely when there are no constraint equations for consistency. I think it would help if they use plain language sometimes. Last, the function f that's, that goes from the f space to x space to the y space that is both one-to-one and on 2 is often called the one-to-one correspondence between x and y or bijection. We saw in section 5 of chapter 1 that UA or into Rn is one-to-one and on 2 precisely when A is non-singular. And non-singular means that the determinant equals 0. Or is that when it's singular? I have to check that again. As we just saw in proving the associativity of matrix multiplication for an n by n matrix A and an n by p matrix B, ABC equals ABC for every vector C. We can now rewrite this as mu ABC equals UA UBC. All right, so let's write this. Associativity says A, B times vector C equals A times B vector C. Doesn't matter how you multiply it. And if C is in the P space, we can say that the function A, B onto C equals the function A times the function B C vector, which equals the function A within the function B C. And this would be one of those symbols from back in the day where it's like a function within a function. So you do B, then you do A. So a function of a function. So this one is saying like this is the function of a function form. The function B works on C, and then A works on the result of that. So a function within a function. But the latter notation denotes Oh, there you go. Composition functions. That's what it's called again. Forgot the precise name. But the latter denotes, well, the latter notation denotes composition of functions. Of course, this formula is the real motivation for defining matrix multiplication as we did. In fact, one might define the matrix product as a composition of functions and then derive the computational formula. Now we know that composition of functions is associative, even though it is not commutative. So addition doesn't work with uh, composition of functions. So F, G, so you do G, then you do F. So you do G, then you do F, and then both of those do H is what I'm seeing. From which we infer that these functions do the same. You're not AB, right? And so and this is in our normal matrix notation. This is how we should understand matrix multiplication and its associativity. Remark, mathematicians will often express the rule mu AB, mu A, mu B as a composite schematically by the following diagram. So our P to our N and our N to our M, all right? I like it. So basically, going back to this, P is going to N. Well, I don't think the P, N, and M there release anything previous. We just have to know that this is transforming something from the P space to the N space, and then from the N space to the M space. And that's basically the entire process of AB. We'll continue to explore the interpretation of matrices as functions in the next section. Now we're at the exercises. So I will save the exercises for Tuesday. And how much time? So what I shall do is take a break, and then I shall be back again. So hopefully you enjoyed. And what we'll do is probably start with 2.2 next time. So that should be the next thing on the list, 2.2, and we're well on our way. So I should be able to finish all of these by Thursday. So I'll see if I can finish 2.2 tonight. And then I could do 3.2 and 1.5 tomorrow, and then it'll be problems on Thursday. So that'll be the plan. So catch me later. I don't know, between 15 and 30 minutes. I'll be back.